Welcome back. In this lecture, we are going to discuss on phase velocity and group velocity. If we consider a plain simple harmonic wave traveling along the positive x direction, then it can be represented either by sine wave or by cos wave. If we consider a sine wave, then we can write it as y equal to a sine omega t minus kx, where a is the amplitude, that means maximum change along any direction, whereas omega is the angular frequency, which is associated with frequency as omega equal to 2 pi nu, and nu is the frequency. That means number of waves passing a point per unit time, where is the separation between two consecutive crests or the separation between two consecutive troughs. And the propagation constant k is represented by 2 pi by wavelength. Now, in this particular case, we observe that only the amplitude is a constant. The quantity within bracket, that is omega t minus kx, is called the phase of that wave. Now, for a particular wave, both omega and k are fixed because omega depends on frequency and k depends on wavelength, and for a particular wave, both are constant. So, unless the wave is changed, these two quantities remain constant. As a result, phase depends only on position or space and time t. Therefore, the phase is a function of space and time. Therefore, we can write the phase as omega t minus kx, and we know that it is a function of space and time. Therefore, we can assume that the phase may change with space and it may change with time. Now, we are only interested in changing phase with time. That is, we want the rate of change of phase with time as del phi del t, and from this equation we get del phi del t equals to omega minus k dx dt. Now, if it is assumed that phase is constant with time, that means with time there is no change in phase. In that case, del phi del t will be 0, and therefore omega minus k dx dt at constant phase will be 0. From that, we can write dx dt at constant phase is omega by k. Now, rate of change of position with time, rate of change of disturbance with time is nothing but the velocity. Therefore, we can write it as Vp, which is called the phase velocity of that wave. And that phase velocity is omega by k. Why do we call it phase velocity? Because this is the velocity with which a wave of constant phase propagates. And that is the representative of the velocity of that wave. Therefore, whenever we consider a single electromagnetic wave propagating in any direction, we consider its phase velocity, and the phase velocity can be estimated if it's a angular frequency and the propagation constant are known. But both of these quantities, omega and k, are very hard to perceive. We cannot visualize those things, though frequency or wavelengths are easier to visualize, or energy, momentum are very well known to us. Therefore, we want to represent phase velocity with the help of those terms which are very easier to us, which we can perceive. And for that, we use de Broglie hypothesis. And we know that from de Broglie hypothesis, the momentum and wavelength are associated. And here we can write momentum as h by lambda, where h is the Planck's constant and lambda is the wavelength of that wave. Now, we can multiply 2 pi and divide 2 pi with this quantity. That means we can write it as h by 2 pi into 2 pi by lambda. In doing so, 2 pi by lambda will be our propagation constant k. And this quantity h by 2 pi is so used in the quantum mechanics that a particular symbol is dedicated for it. We call this h cut or reduced Planck's constant. So instead of h by 2 pi, we can write directly h cut, and 2 pi by lambda is nothing but the propagation constant. Therefore, p can be written as h cut k. From that, we can write k as p by h cut. That means instead of k in the expression of phase velocity, we can write momentum per unit reduced Planck's constant. Similarly, from the energy quantization, we know energy E equals to h nu, where nu is the frequency. And again, it can be written as h by 2 pi multiplied with 2 pi nu. Why? Because we know this 2 pi nu is nothing but angular frequency omega. And h by 2 pi is reduced Planck's constant, so that energy can be now represented as h cut omega. So that omega is E by h cut. Therefore, the numerator in the expression of Vp can be replaced by energy by reduced Planck's constant. So if we replace both omega and k in the expression of phase velocity, we can have Vp equals to E by P. Both energy and momentum are very common to us. And from the relativistic mechanics, if we know momentum, we can easily calculate the total energy. Therefore, phase velocity of the wave, that is the velocity with which a wave of constant phase propagates, can be represented either by omega 2k or by the ratio of energy to momentum. So this is for a single wave. That means whenever, say, a light wave, a single light wave is propagating along a particular direction, then its velocity can be represented by its phase velocity. But if we consider a number of waves, that number can be 2 to 20,000 or more, then what would be the velocity which will represent the group of waves or the wave packet? We cannot say that all these waves are moving with the same velocity. It may not. Then what would be the representative velocity of that group of waves or wave packet? For simplicity, we consider two waves first. And we assume that the two waves have the same amplitude. That is not the basic criteria, but we are doing it for simplicity in calculation. But the main thing is that whatever waves are propagating in the same direction, they have almost same frequency and wavelength. That means all of these waves have slightly different frequencies or wavelength. So if we say delta omega and delta k are the differences between angular frequency and propagation constant among those waves, then that two quantities are very, very small quantities. So we can assume that this delta omega is very small with respect to omega and delta k is very small with respect to k. So if we assume that one wave is represented by a sine wave like y1 equal to a sine omega t minus k, just like the previous case, then the other wave, here we are assuming two waves only for the sake of calculation. Then the other wave can be represented with the same amplitude, but phase will be slightly different because omega and k are slightly changed. So the other wave can be represented as a sine omega plus delta omega t minus k plus delta kx. Here, delta omega and delta k are very small quantities. So these are the individual waves. But when these two waves are propagating in the same direction, they superpose on each other. And from the condition of superposition, you know that the resultant wave has the displacement which is just the sum of these two waves. That is, if I say the resultant displacement is y, then y is nothing but the sum of y1 and y2. And if you look at this equation closely, then it is just a sin c plus sin d formula. It is sin c plus sin d. And we know that sin c plus sin d is twice sine c plus d by 2 cos d minus c by 2. Therefore, if we add them, that will be 2 is a. Then I'm writing sine part at the last. So sine c plus d by 2 cos d minus c by 2. Now, within the sine term, you observe delta omega and omega are associated with each other. And we know from the assumption that delta omega is very small with respect to omega. That means this quantity can be neglected in presence of omega. Similarly, delta k is so small that it can be neglected in presence of k. Therefore, y can be written as the first quantity remains same, that is twice a cos part, then sine omega t minus kx. That means if we say this quantity as capital A, then therefore y can be written as a sine omega t minus kx. So we have started with the sine wave and we get back a sine wave. So we had two sine waves, and these two sine waves when superposed on each other, the resultant wave is also a sine wave. But the most important thing is here that the two initial waves have the same amplitude, and that amplitude was constant. That amplitude was constant with respect to space and time. On the other hand, the amplitude of the resultant wave, that is capital A, is a function of space and time. It has both space and time. So it's a function of space and time. So though the individual waves have constant amplitude, the resultant wave has an amplitude which varies with space and time. And this amplitude becomes maximum, which is twice a, when t and x are 0. And it can be maximum at any other values of x and t. Say it becomes maximum again, that is, it becomes twice a, again at some other time, say t dash, and at other place, say x dash. And under that condition, the cos part must be maximized. That means the phase will be 0. And from that, we can write it as x dash by t dash equals to delta omega by delta k. And since delta k is very small, so under limiting condition, this quantity can be represented as delta omega by delta k. Since x dash by t dash is representative of the velocity, therefore we call that velocity as group velocity. We call that as group velocity. And what is that group velocity? Group velocity is the velocity with which the maximum amplitude of that group of waves propagates. So whenever we consider a number of waves, here we are considering two waves. Instead of two waves, there may be a large number of waves. But whatever be the number, whenever we consider the group formed by all these waves, then that wave moves with a particular velocity, and that velocity is called group velocity, which is actually the velocity with which the maximum amplitude of that group of waves propagates. And we call that velocity as group velocity, and which is delta d omega by dk. And from the same argument as we have talked about in phase velocity, that omega and k are very hard to perceive, we can use momentum and energy to replace those omega and k, so that group velocity can be written as d dE dp, that is rate of change of energy with momentum. Therefore, again, whenever we consider a single wave propagating in any direction, then its velocity can be represented by phase velocity, which is omega by k, or ratio of energy to momentum. And it is the velocity of a wave when its phase remains constant with time. That is the basic definition of that velocity, and that is the representative of the velocity of a single wave. But whenever we consider a group of waves propagating in a single direction, then the velocity with which the whole group propagates, I'm not talking about the individual waves of that group, they may have different phase velocities, but the velocity with which the whole group propagates, the velocity with which the wave packet propagates, that is represented by the group velocity, which is rate of change of angular velocity with propagation constant, or it is the rate of change of energy with momentum. So if we observe it, you observe that here this is your y1, this is your y2. That means these are the two single waves of slightly different frequency or wavelength. You observe this is the wavelength for the first wave, which is represented by y1, and this one is the wavelength for the second wave. And from this figure, you can understand that though they have started from the same point, with propagation y1, y2 are slightly changed due to the phase mismatch. So they have slightly different frequency and wavelength, and as a result, when we consider the group which is constituted by these two waves, then the whole group propagates with a different velocity, and that velocity is called the group velocity. And you observe in case of individual waves, the amplitude remains constant. The amplitude remains constant throughout. In both the cases, the amplitude remains constant. On the other hand, when you talk about the group, the amplitude varies, amplitude changes, because we have seen now that amplitude is not a constant, rather it is a function of space and time. And the velocity with which maximum amplitude moves is actually the representative of the group velocity. And we'll consider that group velocity is the velocity with which the group or the wave packet propagates.